Yes, then. Sir, so I'm starting. Welcome everyone to DevTalks. I'm Sankirth Reddy and I'm thrilled to be here on behalf of GNU Linux Users Group, the official open source and developer community of NIT Durgapur. Today we have a very special guest with us, Mr. Radha Krishna Kavuluru sir. With 8 years of experience as a scientist at ISRO, he's worked on cutting edge technologies like artificial intelligence, satellite data processing, and he even led the project managing the ground segment for NISAR, the NASA ISRO SAR mission. Mr. Radha Krishna Kavuluru sir, it's an honor to have you with us here today.
Thank you so much for having me, Sanket.
Yes, sir. Sir, would you be so kind as to give our viewers a small glimpse into your responsibilities and experience at ISRO?
Sure. So it's been 8 years that I've worked at ISRO. I left ISRO recently. In my time at ISRO, I actually joined right after Indian Institute of Space Science and Technology. After I finished my BTech. I worked on satellite image processing. I worked on developing backend for data dissemination. So we handle petabytes of data. So we use a lot of open source software for handling all of that. And then I also helped ISRO develop some AI models to detect um, phenomenon going on Earth, like cloud, water layers, flooding, and all that. And as you said, I was a project manager for data dissemination systems for NISAR. Yeah.
That's great from you here. That's great to hear from that you, sir. And sir, we have another question. Leading the ground segment for NISAR seems to be a crucial responsibility. Can you walk us through some of the key challenges you faced in data processing from the satellite?
So, yeah, NISR is actually the highest budget Earth observation satellite that the world has ever seen. So one of the most interesting and also complex thing is that satellite is being built by two space agencies, and the coordination between someone who is sitting in America and someone who is sitting in India, and there are teams across the countries. Okay, so we have teams in Ahmedabad, we had teams in Hyderabad, so all of them we have to coordinate with someone who's sitting in USA in their own time zone. So we had meetings in our midnights, like we had meetings at 2 a.m., 3 a.m., so that it's their morning time. And when it's so they also reciprocated. So sometimes they also attended meetings in the night time. So coordination among all the teams across the earth. It's like exactly opposite side of us. So that was the major thing that we understood, that okay, as a team we have to coordinate the best, because again on the satellite we have two payloads, L band and S band. L band is being built by the NASA and S band is being built by ISRO. So when we produce our data sets, they have to be having equal quality, and also the information that has to be generated by the satellite has to have equal information, abundant information in all different applications, in science applications. So producing this miracle, not just with respect to satellite but also on the data processing side, is a very important thing. And moreover, some points like in L band, if you see, there's a good amount of distortion in the electromagnetic spectrum by electron concentration in atmosphere, but on S band it is less. So there is a mutual information exchange that happens from S band to L band in data products. Let's say to minimize the distortion in L band, we can use information from S band. So all of this is a result, and you will see. I hope you will see good data products after the launch very soon. I think it's going to be launched somewhere in the first quarter of 2024, and I hope the data will be soon used. And it's a large scale data, mind you, that NISR mission is the most voluminous data that any Earth observation satellite has ever created. Okay, so it will operate on all Earth, and it will create tremendous data products. So till now, even Sentinel products have been used by the community. Now NSR will come, and it can detect even ground movements on the scale of millimeters. So that's a very very important data set for many applications, and many people are looking forward to it.
It's so fascinating to hear that about that, sir. And so now, with a large number of people learning about AI and software development in order to go for a job at an MNC, what do you think should be the path for someone who wants to learn about AI, software, and to work somewhere at a place like ISRO?
Right. So the paths. So I'm just speaking with respect to ISRO. If you want someone, if someone wants to enter ISRO, the mainstream way is to write the exam called as ICRB, which is of gate level. Okay. So to attempt ICRB, you have to be good at your theory. You have to be good at, let's say, computer science. If you want to come into through computer science, you have to be good at the subjects in your engineering. But again, AI is such a multi-domain experience these days that everyone, not just computer science graduates, but electronics, civil engineering, everywhere there's applications and people are learning for it. So to enter ISRO, I think you have to be good at your basics, your theory, whatever you are studying in your graduation, and then you also have to be good at applied engineering. Okay, so it doesn't mean that if you're good at in ECE or communications, you should not be good at the other side like programming or English person. You have to be good at applied engineering, meaning you have to be good at cross domain applications of your engineering skills. So once you're good at that, you will actually succeed at ISRO. You will actually have a good value and you can actually contribute with your views in building engineering systems.
Sir, it's so great to hear that from you, sir. And so we all know that we are very curious about the James Webb Space Telescope also. We all know that within months of its launch, it delivered some awesome images of the universe, including planets that are light years away. Can you share some insights into the unique challenges that might be associated with JWST data?
Sure. So JWST is the most complex engineering project that we have ever built. Okay, there are multiple reasons to it. So one major thing is, so for example, Hubble. Let's speak of. Hubble was the biggest aperture telescope in space. So what happens is, why we send telescopes to space is, if we have a telescope on Earth to observe stars, there's a very big barrier in atmosphere. So atmosphere all continuously jiggles in between us and stars. So that's why we see stars twinkle. That's why we cannot do good quality observations from Earth. Okay, so even if we have very big telescopes, let's say 10-meter aperture telescopes, the size of your room, the telescope mirror will be there. So even then, the quality will not match with, let's say, 3-meter telescope in space because of atmosphere. So that's why whenever people build big telescopes, they see places like Mount Abu or Leh in India, where there is no or literal less number of clouds and less number of atmosphere because it's at high altitudes, right? So that is one thing. So that's why people send telescopes to space, because there's no atmosphere, there's clean observations every time you can observe. Okay. Now one thing is, Hubble Space Telescope was observing the universe in optical. Okay, so optical meaning red, green, blue, and there are some other wavelengths. Uh, but what we did not have was thermal infrared telescopy or observatory. Okay, so what is the difference is that even in satellites as well, you can see Earth, like let's say Google Maps is there, that is red, green, and blue. You see how your eyes will see it at that altitude. Okay, but there is a large spectrum of electromagnetic waves that our eyes cannot see, but there's a lot of information in it, right? So JWST was built for infrared observations. A lot of light, visible light, is observed by Hubble space. Now JWST has come in infrared. Okay, so using infrared, we can actually see in long wave and mid wave infrared, and there are observatories for that. What is the specialty of JWST? There are two major complexities. One thing is, even to see that infrared observatory, there has to be a very big mirror. Okay, so building that huge mirror to be sent into to be sent into space through rockets is very hard, because there's a lot of stress in rocket to launch, and then the stress itself will deform the mirror, and the accuracy in the mirror has to be on the scale of the wavelengths. Okay, and the wavelengths of thermal infrared is in some nanometers, 1,000 nanometers. So more than 1,000 nanometers, your deformation in mirror should not be there, and that is very hard to achieve in through rockets. So what they did is, they took the aperture, they cut it into segments. Okay, so the JWST's mirror is composed of very very small mirrors, and behind it there are actuators. So using those actuators, they align the small mirrors to form a big mirror. Okay, on and the deformation. So we have to use a hyperboloid or a paraboloid to focus all the rays at the focus, right? So all these hundreds of segments will actually deform themselves using actuators behind them, so that the entire surface union is a paraboloid or a hyperboloid as per design in the order of nanometers. That is the first thing, the major engineering complexity. The second complexity is you are observing something in thermal infrared, which means heat coming from other sources can disturb your observations. Okay, and the major source of heat in space is Earth and Sun because it's in L2, right? So what people did is the observatory, the mirror has to focus away from Sun, so it is actually opposite to Sun. Now, what happens is in space, the sun rays create a lot of thermal gradient. Okay, so when the sun rays hit the satellite on this side, the temperature is very high, and on the other side, the temperature has to be cool to enable your infrared ability. So a grade of thermal engineering has gone into the satellite so as to keep this thermal gradient uniform, and the engineering has to happen. So all the detectors, the telescope, the mirrors, the electronics, or all of them actually work at, I think, hundreds of Kelvin difference. Okay, so there's huge gradient with respect to sun rays falling on one side, then there is pitch black cold on the other side. So that was one of the other complexity, and because of such engineering complexities we have built, humans have built. So now you must have seen recently Uranus photo is also released by NASA. So some beautiful observations that come out of this telescope, space telescopes.
Yes, sir. That's really great to. It's a marvel, sir. Yes, for us. And so, sir, I would like to know whether you were interested in space research from a younger age, or was it something where your interest grew gradually?
Okay, so my story is little tricky. So what I in till 10th class I wanted to join Indian Air Force. Okay, but in 10th class I got eyesight actually, and Indian Air Force does not take people with eyesight. So then it was like because I was interested in technology and I wanted to do something for country. Then I said, okay, I'll join. I will develop my interest in space. So 11th and 12th, my interest was totally in space, and then that's why I joined after 12th to directly in Institute of Space Science and Technology, and from then it has been space from then. So 4 years in IST, 2 years in 11th and 12th, and then 8 years in ISRO, and now also again it's space.
It's really great, sir. So lately, we have been seeing a rise in LLMs, the large language models, as
Yes.
GPT and Gemini. How do you think the scenario changed regarding the use of AI in the field of extraterrestrial research in light of these advanced AIs as compared to 5 to 8 years ago?
Right. So it's a great question actually. So how do we let's say there are two components in this. How do we do extraterrestrial science? There is one thing called exoplanet detection where we see star systems very far away, and then there are methods to detect planets. Okay, I'll tell you one example of how do we detect planets. So let's take a star very far away. We continuously observe it. So there's we get constant brightness. Now our telescopes are not so powerful to resolve planets. Recently we saw one example, but usually speaking, we cannot see extraterrestrial planets. We can only see stars. So if by seeing stars, how do we tell there are planets for that star system? Is you continuously observe planet, you see the brightness of the planet. So what happens is if there is a planet for the star, as you see the stars, the brightness plot will be constant because it's not going to change. The distance is almost same. But when a planet comes before the star, the brightness dips because planet is occulting the star. So a small dip in the brightness will give you an indication that there's some extra body for that star. So then you do more research on it. Then if it's periodic, then definitely there's some other body which is orbiting that star. Okay. One more thing is sometimes if you actually see the spectrum of the star, okay, as you see the spectrum of the star, some it is going to be constant again with not just respect to intensity or brightness, but the spectrum and some other bodies coming in before it. The spectrum actually changes quite a bit in some wavelengths, so that will also give you an indication. But all of this is actually data science, quite frankly speaking. So all these observations are signals with respect to time, brightness, or spectrum, and you have to observe these minute dips. So the basic field of extraterrestrial detection or sciences time series databases. So how do we use in e-commerce, or how do we use in, let's say, traffic analysis? The same algorithms are applied there also. So we detect anomalies. So anomaly detection is something that the field is growing. So even let's say in industrial this thing also, you want to detect anomalies in, let's say, footwear industry. The field is growing. The same algorithms can be applied here also, and that's how it's growing. So you take an algorithm, adopt it to physics. That's it. So so LLMs are basically for text-based things, right? But on the other side, there has been visual transformers that have been growing now. Gemini, or let's say Open ChatGPT 4, they have multimodal inputs. So you upload an image. How do they take it? Is through some kind of vision transformer built into ingest into the multimodal network. So here also you can build vision transformers to detect some things, because these are again observations, time series databases, or you can even say telescope photographs. So again, this is multimodal. Either you take a signal or you take an image and you kind of detect anomalies. That's how it happens.
Sir, it was the you have explained it very great, very nicely, sir. And sir, as most of our viewers are soon to be software developers, and what are the career prospects for software engineers in upcoming projects of ISRO? Which fields have more traction in space sector?
Right. So actually, when we speak of space, the thing people tell is every engineering graduate has an opportunity. Okay, right from civil engineering. If you are a civil engineer, you can have opportunity in building systems to detect flood detection, building systems to detect areas where construction can happen from satellite imagery, to building, you know, trusses and you know you know frames for rocket and all that. Okay, so even in building a rocket, there's a lot of civil engineering concepts that are taken from that. There is equal amount of opportunity in triple E or electronics or computer science or mechanical engineering. Every engineering you take, even biology, physics, maths, everyone are there at ISRO. Okay, so the career prospects are quite good for everyone. And just to give you an idea, you can just go to the ISRO careers website and see there are notifications quite across spectrum. Okay, so that should give you an idea of what are the career prospects. But with respect to software engineers or open source software, in space, open source software is used a lot. Okay, and that is because building software that essentially others have built and tested in the complex domain is redundant. So entire space community uses and feeds off each other's software. Okay, so taking that into perspective, I think all the budding engineers can put their focus on being theoretically good. Okay, because building software is good, but building software for a purpose in an engineering domain needs quite good theoretical skills. Okay, so I can build a GUI today, but what the GUI will do is domain specific. So building something for an e-commerce is basically handling databases, while building some mission analysis software is building GUI by running mission propagation models in the background, which is basically physics and math. So what I would say is be good or be inquisitive and curious about physics, maths, and also be good in software. Because if you know physics and maths but not software, you will not have respect anywhere. Even in ISRO, almost everyone should know programming. Okay. But if you know software, you don't know physics and math, again there's no respect. If you know everything, or if you're curious about everything and if you can learn, that's good. So that's the first quality that you should, even if you don't know, you should be ready to learn.
Yeah, that's great, sir. Yes, sir. Sir, this is a curious question. Private firms in space sector are getting more prominent in foreign countries. Will the scenario change in India too?
I think it has already changed. Indian space policy has come out 2 years back, and government has recently allowed people to venture into space science. So we've got firms who are designing launching rockets. We have firms who are launching satellites. We have firms who are building ground antennas for data downlinks. So the scenario has already changed, and I think what I've read, there's already been $300 million investment in Indian space sector. So that's a good sign, and I think the scenario has already changed.
Yes, sir. And we have a small different question. So, sir, you used AI with satellite data processing, right? Can you share an example of how AI is actually enhancing our understanding of our planet, even distant celestial bodies.
Right. So, AI, so using satellites, especially Earth observation satellites, we use that to not just monitor but also study what is happening on Earth. Recently, I can quote you an example. Microsoft has come up with a model which can detect clouds movement and climate change. Okay, so you may, this is a very high level abstraction. I'll tell you why that is complex. Okay, so numerical weather prediction as a technological domain, it's very hard. Okay, so that's why you don't see weather prediction quite far away. So for 7 days or for 3 days it may be accurate, but for 10 days, 15 days, or even 1 month, you cannot predict when it will be. Okay, that is because innately weather as a system is chaotic. Okay, so if you change the initial conditions, the output after 7 days will be drastically different than your normal simulations or numerical weather integration models. So to model chaotic systems, the best system that humanity has ever invented till now is AI, because AI can understand the nuances and can try to predict from the terabytes of data that we've already captured. Okay, so to understand how weather will change in, let's say, 15 days to 20 days, today the model is able to give you a better prediction than our traditional numerical weather integration models. So in a way, AI has learned physics and has been able to model physics better than us. So that is a great example of how you can use satellite data for weather prediction. But there are many other things. Like for example, if there's a disaster today, like for example, there are floods in Chennai. So what happens? We have to understand what is the damage, which are the areas that have affected Chennai. So what we do is ground service, but it takes a lot of effort. But what happens is when you have satellite passes, all you can do is apply AI models, and right in 5 minutes you can get very high resolution map of flood coverage and where you have to take action. So all of this information is actually done and used by our disaster management authorities, and then they send people, evacuation forces and all that. So this is another example. The other example also I want to give is in the field of agriculture. Okay, so in agriculture also a lot of new innovations are coming up with respect to satellite imagery. Today there are models and there are private firms who are already working on this, who can give farmers a better advice on which crop do they have to sow in which time of the year. Okay, so that they get a better yield. And because they have all these statistics across India, they are also able to offer them better insurance premiums on their crops. Okay, competitive. So if I know that this, if he sows wheat today and that's going to grow a better yield, I can offer low insurance premium than the market. So a lot of these things are being factored into from satellite imagery, and good competitive models are being built up. So that's how I think the whole model is going. And I just gave you three examples, but almost in every other ministry, like urban development, people are monitoring new buildings, collecting taxes, and every other ministry, it uses satellite data, and there's scope for n number of applications.
Yes, sir. Yes, sir. We all of the applications are real life users. It was great that to hear. And sir, we have seen your LinkedIn profile, and you have mentioned about Antarctic space exploration, and we have even saw the post. Can you share your experience there?
Sure. So it's not Antarctic space exploration, but so I'll tell you, my background is I went to Antarctica from when I was in ISRO for 4 months. We have a ground station there. So what we do is basically satellite. So polar satellites. What happens is these orbits of satellites are from North Pole to South Pole. Okay, so I'll just give you an example. So as Earth is here, the orbits are pole to pole, and Earth rotates in between. So that's how, even if the orbit is constant from north to south, because Earth is rotating, we can see tomorrow. For example, today we see India in this orbit. Tomorrow we may see Saudi Arabia, and then again, because Earth is rotating, the next day probably we can see Atlantic Ocean, then South America. So Earth is rotating. But what happens is this orbit is from North Pole to South Pole, and the areas are changing. So, for example, if you have a ground station in India, the footprint, today the pass may come, okay, but tomorrow, because Earth is rotating, it may not come, okay. But what points are constant on this orbit is North Pole and South Pole. Okay, so if we have a ground station there, essentially satellite will collect the data on the Earth and will definitely go to pole, so we can download the data there. So that is the concept of ground stations in North Pole and South Pole. Many countries have this capability. India also has, but other than that, India has two different stations, Maitri and Bharti, and there are n number of activities happening there. So when I went there for 4 months, I went through an organization called NCPOR, which is our India's Polar Research Center. Okay, it is from Ministry of Earth Sciences. So over there, like for example, if you are having some research idea that you want to use polls for understanding Earth or understanding something, biology, etc., you can pitch them. And there is every year they collect these ideas and pick out research proposals. And whoever is having a good idea and good utility in the research, they will fund them and send them to Antarctica. So they do their research there. So on that way, I met a lot of good people. Like for example, I met a zoologist who was researching algae growth in Antarctica because there is no human presence there. The algae actually evolved from the planet. So when Antarctica was there in the history to till day, algae has evolved. So he was studying the evolution of algae and microorganisms in the water there. So that is there, and there is a good project called drilling project. So you can take ice cores. So Antarctica has kilometers of ice piled up. So you can take drill the ice core and bring out the ice core. So from the depth of the ice core, it will tell you the history of Earth because all this ice layer is coming every year. So if you let's say 1 kilometer back ice, if you analyze, it will probably give you information about 10,000 years back at what was the composition of atmosphere then, what were the composition of nutrients or anything like that. I don't know the technical aspect of it, but that's what they do, right? Ice core drilling. So ice core project is there, and there are multiple things like that. So all that research happens at Antarctica, and we have two stations there.
Sir, your experience is an unmatchable experience, sir. We really fascinate that too. Sir,
Thank you.
we we have a small question which is a little about space. Sir, how far are we as a species from establishing a permanent presence on another planet? Is it our destiny to become a dual planet species?
I think personally, and this is my personal feeling, that um, we are born to expand. Okay, and this is my personal feeling. From childhood, I've been hearing stories of how humans have, you know, discovered India, discovered North America, discovered that Earth is round, and I don't see in let's say 3050 the same stories will be read by someone that someone has established a base on Mars, someone has established a base on Europa, okay, or Io or Titan, and they have discovered some life there. I mean, there is no reason that we should not go. I think we are born to explore. See, personally feeling I don't see a meaning for life as a whole humanity other than exploring universe. Okay, so that's the absolute reason I believe that we exist for, and I think that's how we will be going forward.
Yes, sir. It's just the all the possibilities are limitless, right?
Yeah.
And so so we have a slightly tricky creative question.
Okay.
What if a solar system with its planets? What if a solar system with its planets is like an atom,
Okay.
and every Big Bang theory simply describes the formation of one such atom? And could there be other Big Bangs happening right now, creating more such solar system atoms? And could time travel be a form of interatomic travel?
It's a great question, very abstract question. I don't think anyone has answer for it. Okay. Today we are not in a state where we can talk about what is outside our universe, but we definitely have. So quantum mechanics as a theory has put all these questions in our minds. Okay, and how do we explain quantum mechanics is something everyone is debating till now. Okay, so what does quantum mechanics tell us is space or vacuum as we think of is not really vacuum, but there are particles coming in and out of existence. Okay, and deeper and deeper, the universe is not deterministic. So if we know initial state, we cannot tell that this will be the state at after time t. There's some probabilistic behavior of this universe, and there's no explanation for that. So there have been multiple theories of how they can explain this, but there are no feasibility for proving any of this explanation. So one explanation was every probability or every thread that we get from an initial state is a separate universe. And because it's a probability, we are in a probabilistic universe, and there's another thread where every other event is possible. Okay. That said, your notion of thinking that solar system is an atom is quite possible. The only thing is someone has to prove it, and the basis of how do we prove it scientifically is also not yet understood. So it may well be possible that your notion and thinking of it is correct. And on a grander scale, if you see universe, you come out of solar system, there is a galaxy. You come out of galaxy, there is superclusters. You come out of superclusters and you see the image. The simulation is already there. It is like a neural network. Okay, so everything, gravity is binding everything as strings. Okay, so all the galaxies are forming clusters, and all the clusters are forming superclusters. There are threads everywhere. So it is just like a web, and that web can be a spider web in some universe. We have no idea, right? So some proving that is difficult, but yeah, I think the fascination that we are just a small part of whatever we are existing is something that we should always have, and we should always remember that we are no one, and that's how I think we should start exploring and start finding out answers. Yeah.
Yes, sir. It was a tricky question, and it was a creative one, right? And yes, sir. So some and about questions. So as you said, quantum computers, quantum as we. How do you think the next few years are going to be affected by quantum computers and using of qubits?
So initial versions of quantum computers have already come out. Google has it, Amazon has it, IBM has it, but it is in many inertial stages. I per se, I know a little bit of quantum physics. I've never worked operationally on it. I wanted to explore it. Okay, so I am also kind of very beginner in this field, and whatever I have seen, the kind of computing that we can do today is very very specialistic and algorithms. So quantum computing today is an intersection of three fields. There is physics is there, algorithms is there, and maths is there. Okay, so probability, everything is very interconnected, and there is only few algorithms that can take advantage of quantum computing today. Okay, so I think in coming years, let's say 3 4 years, I think there's a good amount of probability that we will expand of our understanding and also on our applications of quantum computing. One thing, and the other thing is already, let's say services like AWS, GCS have rolled out quantum computers as a service. Okay, so people today in research institutions are already using them and evaluating these for different applications. So good research must be coming out.
Yes, sir. And yes, sir. Then that almost brings us to the end of the session today, sir. So before concluding, I would like to thank you for sharing your insights with us today, and it was great to have you here, sir. And shall I? Yes, sir. And to all those
Thank you.
watching, and to all those watching, do check out Radha Krishna Kavuluru's LinkedIn profile. Link is provided in the description below. And I also want to thank everyone for joining our session today. We hope everyone enjoyed today's DevTalk session. And sir, is there any experience that is your most favorite experience till today? We would like to listen to that, and we'll end the session today.
Right. So one thing I'll tell you. So Antarctica has anyways been lifetime experience. I hope very few people get such opportunities, and that is there. But one thing I'll tell you as an experience. I always worked on satellite image processing. Okay, and theoretically, when we read textbooks, when we read papers, and we implement it, we get a good understanding, and we can get the outputs, and we can see. But one day, in the initial days of my career, I think the second year after joining ISRO, I got an opportunity to visit the facility where we actually make satellites. Okay, so satellites are made of different components, but the basic thing is we think satellites as cameras, but the important thing is they have telescopes. Okay, so just like how we cannot see good stars just with cameras, we have to use telescopes. That's how satellites at 500 kilometers, they want to see Earth, they have to use telescopes. Okay, so optics is very huge. Okay, and then there are sensors. So the day that I saw the optic system built for satellite, I actually understood what my code meant that I wrote in last 1.5 years.